Good morning, students. Today I shall start the second part of this infrared spectroscopy. Since this is a very long chapter, so I shall discuss this chapter in part wise, and today it is the second part of this infrared spectroscopy. In previous lecture, that is in part 1, I had discussed about the basics of infrared. What is the range of infrared and how it interacts with the matter, what are the different types of spectrum which is obtained, and what are the conditions which is required for obtaining an IR spectrum of a substance. So today we will start the theoretical part. Due to the infrared radiation, transition takes place among the vibrational energy levels as well as among the rotational energy levels, because the energy of infrared is more than the energy of microwave. Therefore, this spectroscopy is called as vibrational rotational spectroscopy, and spectrum is called vibrational rotational spectrum. Very clear? However, if only vibrational energy changes is considered here, then it will be called as pure vibrational spectrum. So, first of all, here we will discuss pure vibrational spectrum. Now, in order to know the energy required for the transition among vibrational energy levels, we will have to solve the Schrodinger wave equation, which is like this: d2 psi by dx square plus d2 psi by dy square plus d2 psi by dz square plus 8 pi square m by h square e minus v into psi. This is the basic equation of Schrodinger wave equation in 3 dimensions. X, y, z are coordinates, Cartesian coordinates. Psi is the wave function. M is the mass of the particle or mass of the system. H is the Planck constant. E is the total energy of the system. V is the potential energy of the system. So this equation can also be written in this form. This is the operator form, or it is not truly operator form. Only these 3 terms are written in the form of del square, that is Laplacian operator, and this mass is converted into reduced mass mu. The rest terms are same. Here the details are the different terms. Mu is the reduced mass, E is the total energy, V is the potential energy. Del square is called Laplacian operator. d2 psi by d square plus d2 psi by d square plus d2 psi by d2 psi by dx square plus d2 psi by dy square plus d2 psi by dz square, and psi is the wave. Now, in order to know the energy value, we must know the value of potential energy of the system and also the vibrational frequency omega in per centimeter or hertz. So, for calculating the potential energy, we have to take a system. Let us here in the figure we have taken a diatomic molecule. A and B are atoms of this diatomic molecule. M1 and M2 are the masses of A and B respectively. And here this is at the equilibrium distance represented by Re. R is the distance when the bond is stressed. Everything is written. So, let the vibration be assumed to be simple harmonic. That is, it is the case of simple harmonic motion. Simple harmonic motion is a case like this. Suppose it is suspended through a thread, and if we want to disturb it in one side, then this is the position of this. This is the position of this bob. Now, after reaching at this position, it comes to its initial position and then goes to another position in the right hand side, and this type of vibration is set. This vibration or this motion will be called a simple harmonic motion when this angle theta is less than 4 degree, if it is more than 4 degree, then it will be not called as simple harmonic motion, or it will be called as anharmonic motion. This motion is like this. When the bob starts at this equilibrium position, it goes to this position, again comes to the equilibrium position, again goes to the right hand side on this position, and then comes to the initial position, and then it completes one complete vibration or one complete cycle. This can be represented on a line also. Suppose bob is at this position, it vibrates to this position, again comes to the mean position, again goes to the right hand side at this position, and then comes to the mid position. So here on one line we can represent the motion of that simple harmonic. From figure, one thing is we have to clear that when it is in stressed position like this, this distance x1 and this distance x2 are the distances which is obtained after the stretching of the bond length. So here this x1 is the displacement of the bond on left hand side, and x2 is the displacement of the bond on the right hand side. Minus sign is taken here because if we take plus sign or positive sign on moving on right hand side, then we have to take a negative sign while moving on the left hand side, and therefore here x1 is associated with minus sign. So total displacement x will be equal to the extra distances obtained, addition of these two extra distances obtained after stretching, that is x1 plus x2 or minus x1 plus x2, and this x will be equal to r minus re, which is clear from the figure. This r minus r will be equal to the x1 plus x2, and that is represented by x, total displacement. Now we have to calculate the potential energy. We have to calculate the potential energy of the system. For this we take the help of Hooke's law. This topic is in physics. So from physics, simple harmonic motion, we have taken this Hooke's law. According to Hooke's law, F is proportional to x. That is, F is the restoring force and this x is the displacement. So restoring force is directly proportional to the displacement but in opposite direction. Therefore, a negative sign is taken. This is also clear from this figure that suppose bob has come at this position, then the force which is operating for restoring in its initial position will be in this direction, So force is operating in this direction, but displacement is in this direction. And force is operating in this direction. Therefore, this F, that is restoring force, is directly proportional to x with a negative sign. When we replace this proportionality sign with equal to sign, then a constant is required, and k is the proportionality constant and is called this force constant. Now again, this force is equal to, according to the physics laws of motion, this force can be written as mass into acceleration, and when mass is represented by m, acceleration will be represented by d2x by dt square. Sorry, here it is dt square. d2 square. So mass into acceleration, this will give the value of force. So here in this equation number 2, we have written mass into acceleration is equal to minus kx, and this acceleration will be equal to minus ks divided by m. Now for mass m1, this equation can be written as m1 d2x1 by dt square is equal to minus kx. Here it will be not x1, here it is the total displacement. And for mass m2, we will write m2 into d2x2 divided by dt square is equal to minus kx. Again kx, not the kx1 or x2. Here it is total displacement. So according to this equation, here we can write this m1 will go in the lower side, and here this m2 will also go to the lower side. And again for acceleration, we write d2x by dt square is equal to d2 by dt square in bracket. We write x2 minus x1 for x, because from equation 2 x is equal to x2 minus x1. So from equation 2 here x is written as x2 minus x1. So d2 by dt square of x2 minus x1, when it is solved, this will give 2 term, and when these values are put here, we get this type of expression. When we take common, we will get this type of expression. Here we take LCM, and finally this term is equal to the reduced mass m1 m2 divided by m1 plus m2. So this term in the bracket is equal to 1 by mu. Now this acceleration d2x by dt square is equal to minus k by mu into x. On rearranging, we get equation 3. On solving equation 3, this equation 3 is nothing but it is a differential equation of second order. This is, here comes mathematics. So this is a differential equation of second order, and when this equation is solved, we get this type of solution. X is equal to, solution of this equation 3 will be obtained in terms of x. So x is equal to a sine under root k by mu into t plus c, equation number 4. Now the general equation, when solved for simple harmonic motion, this gives in the form of equation 5, that is x is equal to a sine twice pi omega into t plus c. This is equation 5. So when we compare these two equations, equation 4 and equation 5, we get the relation. Everything is same except these two. So twice pi omega will be equal to under root k by mu, and therefore omega is equal to 1 by 2 pi k by mu per second. And however, in terms of wave number, we can write nu bar is equal to 1 by lambda is equal to nu by c according to this equation. And if nu, that is frequency, is taken in terms of omega, that is if we replace nu with omega, then we will put the value of omega, and final equation we will get twice pi c under root k by c per centimeter. Now this is we have to calculate two terms. One thing was omega and another thing was potential energy. Now we are going to calculate the potential energy V. So from definition, the restoring force is related to potential energy with this equation, that is F will be equal to minus dV by dx, where V is the potential of the system. Negative sign is used because restoring force acts in a direction opposite to the displacement. Now when we put the value of F, which I have written in the form of Hooke's law, here it is Hooke's law, F is equal to minus kx minus equation 2. So F is equal to minus kx. If we put F is equal to minus kx, so automatically minus sign cancels out from both sides, and when we simplify this equation, we get dV is equal to kx into dx. Now if we integrate this equation, then we will have to put integration sign on both the sides. Here it is dV, k is the constant, that is 4 constants, so it can be taken out from the integration sign, and now it can be integrated. So integration of V is dV, and integration of x dx is x square divided by 2. Now here it should be noted, or there's confusion, that here we have not taken any integration constant. Here not written any integration constant. Suppose here we take an integration constant c, then what happens? We take an integration constant c, then we have to calculate the value of this c. So the value of c can be calculated by putting the initial values of v and x. So when x is equal to 0, V is equal to 0. So when x is equal to V is equal to 0, therefore C is equal to 0. Automatically this term vanishes, and therefore here I have not written the integration constant. Now the solution of this equation becomes V is equal to k x square by 2, or V is equal to half kx square. Now when this value is put in Schrodinger's wave equation, that is in equation 1, here this value of V is put del square psi plus 8 pi square mu by h square E minus half kx square instead of V, that is potential energy. And now the allowed solution of this equation 8, that there are so many solutions of this equation, the differential equation of second order in 3-dimensional, and when solved we get so many solutions, but only certain solutions are allowed. So we have written the allowed solutions. So the allowed solution of this equation 8 is given by E is equal to h nu V plus half joules, where this V corresponds to the vibrational energy, and this V is the vibrational quantum number having values 0, 1, 2, 3, 4. H is the Planck constant, nu is the frequency, and the unit of this h nu will be joule, because the unit of Planck constant is joule second and the unit of this nu frequency is per second. Therefore unit of this h nu comes as joules, that is this energy is represented in terms of joule. Our calculation for the energy in vibrational energy levels in the transition of vibrational energy levels. Third part of this third spectroscopy I shall discuss onwards from this position. Okay, thank you.